Always good to just do a little recap of what a line of invariant points is and what an invariant line is. They're subtly different. So let's imagine I do a reflection about y equals x. Then the line of invariant points would actually be the mirror line itself. Because when you reflect that point that I've just highlighted in the mirror line, it stays exactly where it is. They map towards themselves. That is what an invariant point is. You can get other transformations. They don't have to be reflections, but then you'll get like a line of invariant points where every point on the line, when applying the transformation, will stay exactly where it is. And what you typically do, well, not what you typically do, what you do is you take your matrix and you multiply it by a general position vector or coordinate, if you want to say it like that, and you get back to the same thing, and then you solve for you get y in terms of x, and you do it for two equations and just check they're consistent. That is our line of invariant points. Now, invariant lines are different because well, I'll come back to they're different, but there are some overlap. Right, with an invariant line, in general, when you have a point on it and you do the transformation, let's say again it's a reflection of y equals x, it now would map over here and it stays on the line, but in general it's going to move to somewhere else on the line. So it doesn't stay in the same place. So with a reflection, any line that's perpendicular to your mirror line, in this case, I could draw y equals minus x, I could draw y equals minus x minus 2, but you take a point and it's going to map over to here. That one's going to map back, but they're all going to stay on the line. And so actually you'd get y equals minus x plus c as your class of invariant lines. Now you'd actually also get the line of invariant points as an invariant line, because if it maps to itself on the line, it's still mapping to somewhere on the line. So every single line of invariant points is also an invariant line, but it's not true the other way around. All right, it is a little bit confusing, but I'm hoping like this is not the first time you've seen it, of course. So hopefully it's just bringing back those ideas. Now we're going to say that our invariant line is going to be y equals mx plus c. That's as general as it gets, a general straight line. And then after we've applied our mapping, oh, sorry, so here we've got a coordinate of x, y. So after we've applied our mapping, we're going to get a new coordinate, x dash, y dash. Sometimes I use a capital letter, but here I'm going to use a little dash. And the point is, it's still going to be on this line. So then y dash is going to equal mx dash plus c. And this is how we calculate the invariant line. So invariant line satisfies, it's just a little equation that you need to know, but I'm going to try and explain where it comes from. So we're going to take our matrix, we're going to multiply it by x, y. However, we know for our invariant line that y is equal to mx plus c. So I'm not going to write y down, I'm going to write down mx plus c. That is my y value on my invariant line. And then my x value is going to map to my new x value, x dash. And my y value is going to map to my new y value, y dash. But check it out, that is mx dash plus c. And this is your way into any question where you're asked to find the invariant lines, or in this case, show that there's no invariant lines. If you're ever asked to show that something was invariant line, then what you'd be doing is just substituting your invariant line in the same sort of way and trying to get to this, but I'm not going to talk about that here. And let's multiply the matrix out. We're going to get a set of equations. We're going to show there's no solution. So I'm going to get 4x minus 2mx minus 2c, because I'm doing this row by this column, and that's going to equal x dash. So that's the first bit sorted. And then keep that, and then do the next row. I'm going to get 5x plus 3mx plus 3c, and then that is going to equal mx dash plus c. Of course, this is much more complicated than finding a line of invariant points, but there's a process that works every time. Because what we're going to do now is replace this x dash by this, because then I'll just get an equation involving m and x and some constants, oh, and c, of course, but we get rid of the x dash. Therefore, 5x plus 3mx plus 3c is equal to m times 4x minus 2mx minus 2c plus c. And remember, this is true for all values of x. So really, I want to put an identity here. True all x. We're not solving this to find a particular value of x. It's true for all x. I'm just going to multiply the bracket out on the right. So I get 4mx minus 2m squared x minus 2mc plus c. And this, you can try and collect all the x's on one side and all the constants on one side. I don't worry about doing that. What we can now do is compare coefficients. Let's compare the coefficients of x. Because this is true for all values of x, it must be that the coefficients equate. So 5 plus 3m is going to equal 4m minus 2m squared. And the same goes with the other ones. I've got 3c minus 2mc plus c, but I'm not going to worry about that. I'm just going to deal with this for the moment, because I've now got an equation just involving m. It's a quadratic in m. And let's see what the solutions are. By the way, we're going to show that there are no solutions, and then hence there's no invariant line. So we don't actually need to deal with the other one. But in general, if you're finding it, you would find your values of m from here, and you would sub it back into the other equation that you get by equating these, and that would help you find your c. Right, 2m squared, then it's going to be minus m plus 5 is equal to 0. Let's just look at the discriminant. B squared minus 4ac. Remember, we're trying to show there's no solutions. So if we can show the discriminant's negative with there, it's going to equal 1, because that's just minus 1 squared, minus 4 times 2 times 5. This is clearly negative, but it's going to be minus 39. Less than 0, no real solutions. And that is it. Therefore, I've forgotten A. Sorry, for transformation M, for transformation M, there are no invariant lines. It's one of those questions that is, you do this when you cover it in the first year of the A level, and then you don't come back to it. And it's easy to forget, but that's why you're here, I presume. Like practicing these, like find more practice questions where you're finding the invariant lines, questions where you're showing that such and such is an invariant line. It all uses this idea, but in slightly different ways. Well done.